Remember, Coulomb's law is simply the mathematical description of the electrostatic force between two charged particles. This law can also be applied when multiple charges are present and acting on each other. This, of course, makes things a little more interesting. Say we have three charges that are all aligned as shown. What is the force being exerted on each of the individual charges? What we have to look at here is the force acting on an individual charge by each of the others. For example, charge A is being repelled with some force by charge B, but at the same time it's being attracted to charge C with some other force. Remember that forces are vectors, and that includes forces created by charges. So the net force acting on charge A will be the vector sum of the forces due to charge B and charge C. This is often referred to as the principle of superposition. When dealing with multiple forces, it is helpful to use double subscripts to denote each force involved. The first subscript refers to the particle on which the force acts, while the second subscript refers to the particle that is exerting the force. So FAB is referring to the force exerted on particle A by particle B. Now, if we take our information and find the amount of force that B exerts on A, we find positive 225 newtons. Since we are calculating the magnitudes of forces, we can omit the signs of the charges. Once we have our magnitude, we can go back and assign the directions. Notice that this will be a positive force because A and B both have a positive charge and will repel each other, meaning that particle A will be pushed to the left by particle B. In this case, we have just defined the left as our positive direction. Now, particle A is also being affected by particle C. In this case, the charges are opposite, so the two particles are attracting each other. When we determine the force of C on A, we find it to be negative 200 newtons. The negative here refers to the right direction since particle C will be exerting an attractive force on particle A. So particle B is pushing particle A to the left with a force of 225 newtons, while particle C is pulling particle A to the right with a force of 200 newtons. The net force acting on particle A will be the sum of those two forces, and since they are in a straight line, we simply add them together. So the net force acting on particle A is 25 newtons to the left. Now, if we look at particle B, we can see that particle A is exerting a repelling force on it. According to Newton's third law, this force will be equal and opposite to the force that it exerted on A. The force of B acting on A was a positive 225 newtons. So the force of A acting on B will be 225 newtons to the right, or a negative 225 newtons. Now particle C is negatively charged, so it will have an attractive force on particle B. This will pull B to the right as well. When we do the math, we find that the magnitude of the forces is 719 newtons. In this case, both forces acting on particle B are acting to the right, so the net force is 225 plus 719, which turns out to be 944 newtons to the right. Now we get to the forces acting on particle C. Particle A and particle B are both the opposite charges of particle C, so C will be pulled to the left by A and B. Now we have already found the force of C acting on A and C acting on B. We can again apply Newton's third law and say that the magnitudes of these forces are equal, but the directions are opposite. So the force of A acting on C is a positive 200 newtons, and the force of B acting on C is a positive 719 newtons. So the net force acting on particle C is 919 newtons to the left. So to summarize the net forces acting on these three particles, particle A has a net force of 25 newtons acting in our positive direction, which in this case is to the left. Particle B has a net force of 719 newtons to the right, and particle C has a net force of 919 newtons acting also to the right. Now keep in mind we could have just as easily assigned the right as the positive direction. The initial positive and negative does not matter, but it is important to keep them consistent as you work through a given problem. Now let's make things even more interesting. Of course, in real life, the chances of particles lining up in a perfect line for us is probably pretty slim. In this case, we have to look at the x and y components of the overall force acting on each particle. So let's look at particle A. Particle A is being pulled to the right in a straight line by particle B, since opposite charges attract each other. This line is pretty easy to imagine since we drew it in a horizontal fashion. The force being exerted on particle A by particle C is also acting in a straight line, just not along the same line as particle B. Since A and C are the same charge, they will be repelling each other. So the force acting on particle A because of particle C will be going off up into the top left corner at some angle. So let's start with the force of B on A, since it is a nice straight horizontal line for us. We have both charges and a distance, and so we can math that out and find the force to be 449 newtons to the right. Notice this time around we assigned the right to be positive. Now let's look at the force of C on A. Keep in mind this is also acting in a straight line, and we can determine the magnitude of this force as long as we know the distance between the two particles. We can find this distance fairly easily by using the Pythagorean theorem. This lets us determine the magnitude of the force C acting on A to be 179 newtons. Now here we don't want to assign a direction because we have already defined the right to be positive, and this force is not acting in just the right or just the left. Now since we have two forces acting in different directions, we need to resolve the AB forces and the CB forces into x and y components so we can add them together to find the resultant. The vector for the force of B on A is pretty straightforward since we defined it as moving along the x direction. So the x component of the force of B on A is a positive 449 newtons. The y component is 0 since it's only moving to the right and there is no up and down motion to it. The force of C on A, however, is a bit more work. Before we can determine our components, we need to figure out what angle the force is acting. A little trigonometry here with our tangent function, and we find that the angle is 27 degrees above the horizontal. The x component is adjacent to the angle, so we're going to use the cosine function with our angle and force magnitude. We then find the x component of our force vector to be 159 newtons. Since it is acting to the left, it will be a negative 159 newtons. The y component is found using the sine function and is acting in the up direction, so we will say it is a positive 81 newtons. Now that we have our components in each of our forces, we can use those to determine our resultant force vector. First, let's look at our x components. The x component of particle B acting on particle A is a positive 449 newtons, while the x component of particle C acting on particle A is negative 159 newtons. The two components are acting in opposite directions, so the two components will be subtracted from each other. The resulting x component ends up being a positive 290 newtons. The y component comes from the force of C on A, which is found to be positive 81 newtons. So that gives us the components of our net force. Those two components added together give us the magnitude and direction of the total force of particles B and C acting on A at some angle, both of which we are finally ready to find. Let's start with our angle. We know the two non-hypotenuse sides of our triangle, so we can use the tangent function. Calculating that out, we find the angle of the net force to be 74 degrees. Note also that this is totally not drawn to scale. Now that we have our angle, we can use either the sine or cosine function to calculate the magnitude of the resultant force. A little rearranging and some calculating, we find the net force acting on particle A to be 1,052 newtons. So going back to particle A, we can visualize the net force acting on the other two particles as being 1,052 newtons at a 74-degree angle from the positive horizontal. Now what about particle B? Particle B feels an attractive force to particle A since they are opposite charges. This force is felt along the horizontal to the left, so it will be a negative force. And we found the magnitude of this force earlier to be 449 newtons. So the force of particle A acting on particle B is a negative 449 newtons. Particle B also feels a force due to particle C. Particle C is nicely aligned with the vertical direction for this orientation, we can say down, which means the force is acting in the negative direction. Since these particles are opposite charges, the force will also be attractive. Following the math for this force, we find it to be a negative 719 newtons. This gives us a nice right triangle right off the bat. We just need to move one of our vectors over so they are aligned head to tail. Adding these two together, we find the resultant vector. So we have drawn our resultant vector at some angle theta. It's always a good idea to start with the angle. So the opposite over adjacent is the tangent function. So punching that in, we find the angle of our net force to be 58 degrees. Now that we know our angle, we can find the resultant using either sine or cosine, whichever is your favorite. Cosine is adjacent, so the x component of 449 over the net force is equal to the cosine of 58 degrees. So we can find the magnitude of the net force to be 847 newtons. Now we can compare the net force acting on particle A and particle B before finally moving on to particle C. Particle C is being affected by the force from particle A along the same path as the same angle that particle A was affected by it. We've already determined that angle to be 27 degrees and that distance to be 2.24 centimeters. So we don't have to go through all of that again. And since the two charges are the same, the force will be a repulsive one felt by particle C along that path with a magnitude of 179 newtons. The force of particle B acting on particle C is an attractive force since they are opposite charges. And again, this nicely aligns straight up with a vertical direction for us. Reviewing the math, we know that the magnitude of the force to be 719 newtons in the positive direction. Okay, good. So now we have the forces acting on particle C. Now we need to find the components. What's nice is that the component right triangle of the force acting on particle C from particle A is the same right triangle that we found for the force acting on particle A from particle C. So the x component is found with a cosine and has a magnitude of 159 newtons and is positive since it's acting to the right. The y component uses the sine function to find 81 newtons in the negative direction. The two vertical vectors are in opposite directions, and as a result, the y components will be subtracted from each other, giving us a total y component of positive 638 newtons. The x component comes only from the force of A on C, so is found to be 159 newtons in the positive direction. Now we can draw our absolutely not to scale resultant vector for the net force acting on particle C. To find the angle, we can use a tangent of 159 over 638 to find a really small angle of 12 degrees. Then use that angle to find the net force of 652 newtons. So putting that all together, we get a pretty good visual of the net forces acting on each individual particle. So there you have it. When you are dealing with multiple charges, you just have to remember to include the effect of all of the other charges that are acting on it.